Welcome back to Scholars Academy. In everyday life, studying at your desk for 6 hours feels like a massive effort. But in physics, if nothing moves, you've done zero work. To perform work, you must apply a force that results in a measurable displacement. Pushing a heavy block that doesn't budge results in no work. Work only begins the moment that block slides forward. We calculate this using vectors. Work is defined as the dot product of the force and displacement vectors. This gives us the standard formula. Work equals force times displacement times the cosine of theta, where theta is the angle between the applied force and the direction of movement. That angle determines the output. When you push in the same direction an object moves, the angle is 0 degrees. Since the cosine of 0 is 1, your work is maximized. However, if you push at a right angle to the movement, like carrying a heavy load while walking forward, the angle is 90 degrees. Because the cosine of 90 is 0, the work done on that load is 0. After calculating work, we measure the rate of that performance. That is power, work divided by time. The standard SI unit for work is the joule, while its CGS equivalent is the erg. 1 joule equals 10 to the 7th ergs. Dividing those joules by seconds gives us the SI unit for power, the watt. Combining work and power provides the tools to measure the mechanical effectiveness of a system and the specific speed at which forces were applied. Energy is the capacity to do work. In mechanics, we focus on two primary forms: kinetic energy, the energy of motion, calculated as 1/2 mass times velocity squared, and potential energy, the energy of position, calculated as mass times gravity times height. A common error in board exams is confusing the kilowatt with the kilowatt hour. A kilowatt is a measure of power. A kilowatt hour represents power multiplied by time, which makes it a measure of energy. Distinguishing between these two is critical for exam accuracy. This diagram demonstrates conservation of energy. At position A, velocity is 0, so kinetic energy is 0, and potential energy is maxed at mgh. As the ball falls, decreasing height lowers potential energy, while increasing speed raises kinetic energy. The total sum remains constant. While energy forms shift dynamically during motion, the total mechanical budget of the system remains fixed. Consider a 5-kilogram block moved up an 8-meter 30-degree incline by a 50-Newton force. Work is force times distance. 50 times 8 equals 400 joules. Vertical height is 4 meters. With gravity at 10, potential energy, mass times gravity times height, equals 200 joules. This creates a discrepancy. We performed 400 joules of work, but gained only 200 joules. The remaining 200 joules were spent overcoming friction on the incline, creating degraded energy. In real-world mechanics, the work applied must exceed the stored energy to account for these unavoidable losses to the environment. The motion of a simple pendulum is a standard application used to observe mechanical energy conservation. At the extreme positions, B and C, the bob momentarily stops before swinging back. Since velocity is 0, kinetic energy is 0, and the potential energy is at its maximum for the arc. As the bob swings through the resting position A, the height is 0, meaning potential energy is 0. However, the bob reaches its maximum velocity here, meaning the energy has converted entirely into kinetic energy. The total mechanical energy is conserved throughout the entire swing. To summarize, the angle between force and displacement determines the work done. Power is the rate of work, and energy is the capacity to perform it. In any frictionless environment, the sum of kinetic and potential energy is a constant value. Understanding the relationship between work vectors, power rates, and energy conservation provides the required foundation to solve complex mechanics problems on the ICSE exam.